Another application of solving dy dt is equal to a constant times y, or where the rate of change is proportional to the amount, in other words, is in Newton's law of cooling. I have here in this room two objects. The one that's deeper red is supposed to be hotter. And we know if you leave something hot out on the counter, eventually it's going to cool, which means that it's going to be losing its energy over time. So if we assume that this object is small in comparison to the environment, then the object is not going to warm the environment that much. We can assume that the temperature in the environment, we'll call it T sub E for the temperature in the environment, is going to be constant here. Now the temperature, you could think, is a measure of the average energy of the molecules in the air. So if you go into a room and it's cold, it means the molecules in that room are not moving very fast. They don't have very much energy. If it's hot, the molecules in that room have a lot of energy. Now, what's happening if the object is hotter than those molecules, then on average when they collide with this object, they'll be able to steal a little bit of heat. So if they come in at one speed, then they leave with a little longer arrow because they've picked up a little bit of energy. And if the object is hotter, then they'll be able to pick up more energy per collision here. Now, if the temperature in the room is going to stay constant, then the number of collisions per unit time should be about the same, which means that the amount of energy that gets stolen is larger for objects that are warmer than the environment. What we really care about is the difference between if the T is, this should depend on capital T, the temperature, as a function of T, the time. That's going to be the temperature of the object. Okay, and what we need to track really is how much warmer or cooler is the object than the environment. If the object is hotter than the environment, then this will be positive, and if it's cooler than the environment, this will be negative. So what we can say is that the rate of change of y, right? So dy dt is the same thing as dt dt because the derivative of this with respect to t is a constant. So if we look at the change in temperature of the object, that would be dy dt. That's going to be equal to some negative constant times the difference in temperature. So that if y is positive, if this is negative, we'll see a decrease in temperature. And if y is negative, that would mean that the environment is warmer than the object. Then we'll see, since this is negative, a negative times negative will be positive, and we'll see an increase in the temperature. We know the solution to this problem is that y of t is equal to the initial value of y times e to the constant times t. Here the initial value of y would be the value of y at time 0, which would be t at time 0 minus the temperature of the environment, which would just be, I'll call it T naught. It's temperature of the environment. If I substitute this back in, I have T minus the temperature of the environment is equal to y naught, which would be T naught minus the temperature of the environment, times e to the kt. Now we're expecting k to be negative because if y is big, that means the object is warm and we would expect it to lose heat. Whereas if y is negative, that means the object is cooler than the environment and we would expect it to pick up heat. So we think this is a negative number. And we have the temperature is the temperature of the environment plus T naught minus T sub e, e to the kt, where this is negative. So we expect that this will be decaying away. So that if this is the temperature of the environment, if we start off with something hotter than the environment, the temperature of the object will approach the temperature of the environment. On the other hand, if we start off with something cooler, then this is going to be a negative number. We'll have the temperature of the environment minus a bit, so we'll start out below the temperature of the environment and gradually come up or decay onto that temperature in the environment. So this is Newton's law of cooling, where you assume that the cooling has this form. Let's look at an example. I have an aluminum beam that was brought in from the outside cold into a machine shop where the temperature was held at 65 degrees Fahrenheit. After 10 minutes, the beam warmed to 35 degrees Fahrenheit, and after another 10 minutes, it was 50 degrees Fahrenheit. So let's use Newton's law of cooling to estimate how much the beam, what its temperature was initially, how cold it was outside, in other words. Okay, so we've got our model that the temperature should be equal to the temperature of the environment plus the initial difference in temperature between the object and the environment times e to some constant times t. Now in this case we don't know the initial temperature and we don't know what that k should be. We do know that, let's see, after 10 minutes, so after 10 minutes the temperature was 35, and I know we're approaching 65 after another 10 minutes. So there's at 20 minutes, we know that it was up to 50, like this. So we should be able to figure out back here what was the initial temperature of the beam. Well, let's use the information that we were given. We know the temperature of the environment is 65, and we know that if we start here at as calling that time 0, when we first measured that the temperature, 10 minutes after we measured that it was 35 degrees, let's call that time 0, then this would be time 10. If we use this equation, we know that in that case the initial temperature was 35, the temperature of the environment was 65, we have e to the k times 10 minutes, and the temperature of the environment is still 65. We know after 10 minutes, if we started at a temperature of 35, we got up to a temperature of 50. So we can solve this equation. Let's see, if we take 65 away from both sides, 50 minus 65 would be negative 15. 35 minus 65 would be negative 30, e to the k times 10. If I divide both sides by negative 30, I have 1/2 equals e to the k times 10. So the natural log of 1/2 is k times 10. So k is the natural log of 1/2 divided by 10. The natural log of 1/2, since 1/2 is less than 1, we know that's a negative number. So that's what we expected, was that k would be some negative number. Now our question is to figure out what was the beam's initial temperature. So we don't know that initial temperature. We do know that 10 minutes after it came in, so if the initial temperature was whatever it was outside, and the temperature of the environment is 65, and we have T naught minus 65 e to the kt, and we know what k is, and we know we waited 10 minutes and the temperature turned out to be 35, then we can use this to solve for the initial temperature. First thing I do is subtract 65 from both sides to get negative 35 equals T naught minus 65 times e to the kt. The next thing I'm going to do is, or k times 10, the next thing I'm going to do is divide by e to the k times 10. So I'll have negative 30 divided by e to the 10k is equal to T naught minus 65. If I add 65 here, I'll have T naught is 65 minus 30 over e to the 10 times k. Now I know what k is. K is the natural log of 1/2, so I could plug that in there. So I have that the initial temperature was 65 minus 30 over e to the 10k. That would be e to the natural log of 1/2. Oh wait, the natural log of 1/2 is the exponent you put on e to get 1/2, so we have 65 minus 30 over 1/2. Multiply top and bottom by 2, and we have 65 minus 30 times 2 would be 60, and 2 times 1/2 would be 1, so we have 65 minus 60. That would be 5 degrees Fahrenheit for the initial temperature using Newton's law of cooling.